learned how to mark a decimal, integer, and fraction on a number line. But how about marking square roots on a number line? For example, square root of 3.
It's so easy. We can just find out the square roots of 3 by using a calculator and then mark it on a number line. Let me show you. I've got the result.
So what's the result?
It's around 2.44948. If we need to correct it to 3 significant figures, the answer should be 2.45.
The result is not 2.45. You must have got the wrong number. Well, 3 is larger than 1, but smaller than 4. Hence, 3 is between 1 and 4. Square root of 3 should be between square root of 1 and square root of 4. That means square root of 3 should be between 1 and 2. So you'll probably have pressed 6 instead of 3. Now can you try it again to find out what is square root of 3?
It's around 1.73205. If we need to correct it to 3 significant figures, the answer should be 1.73.
But if we need to mark the square root of 3 exactly on a number line, how to do it?
We need to use Pythagoras theorem and property of a circle.
Pythagoras theorem?
Pythagoras theorem was discovered by Pythagoras. Pythagoras is a famous mathematician and philosopher of ancient Greece in the time between 580 BC and 500 BC. Pythagoras is the most renowned for his achievement in mathematics by discovering and proving that for any right-angled triangle, the square of the length of the hypotenuse equals the sum of the squares of the lengths of the other two sides. That means c square equals a square plus b square. In commemoration of Pythagoras' contribution, this theorem is named Pythagoras theorem. Pythagoras theorem is a very important mathematical theorem, and till now there has been more than 400 different ways to prove it. Follow me. We can prove Pythagoras theorem by playing this game.
So, how to play this game?
There are 2 same-sized frames and 4 same-sized right-angled triangles which form a square. Try to use these 4 same-sized right-angled triangles to create 2 squares within this frame. Okay.
Miss Chen, we have done it. There are 1 bigger square and 1 smaller square. But how does this puzzle relate to Pythagoras theorem?
Have you noticed that the areas of the squares are equal to the squares of the lengths of the sides of the right-angled triangle? If the length of this right-angled side is A and the length of this right-angled side is B, then the area of A is A square and the area of the square is B square. Also, if the length of this hypotenuse is C, the area of the square is C square.
So, how can we prove Pythagoras theorem?
Well, I'll give you some hints. The areas of these 2 frames are equal. Think about it. Check out the yellow portion of the 2 figures. Each figure has 4 same-sized right-angled triangles. The area of a triangle equals the base times the height, and then divided by 2 equals AB divided by 2. That means the areas of the triangles of each figure equal 4 times AB divided by 2. As the areas of the 2 figures are equal, C square plus 4 times AB divided by 2 equals A square plus B square plus 4 times AB divided by 2. After the transposition of terms, C square equals A square plus B square, and that is Pythagoras theorem. Or we may directly remove the 4 right-angled triangles away from the 2 figures respectively, leaving the remaining figures. Try to think about the areas of the remaining figures. We can also prove the Pythagoras theorem.
Oh, that is how Pythagoras discovered the theorem.
Well, it is not quite so. His proofs have been lost already. These proofs are actually those made by people of later generations. As a matter of fact, there are many other proofs available. Among them, there's one interesting proof, which is to use the formula of area of trapezium to prove it. Firstly, put the identical triangle horizontally onto the original triangle this way. Draw a line connecting the 2 vertices. Then we make a trapezium. These 2 angles are 2 acute angles of the right-angled triangle. According to the theorem that the sum of interior angles of a triangle is 180 degrees, then the sum of the 2 acute angles equals 90 degrees. That means these 2 angles equal 90 degrees. Also, according to the theorem that adjacent angles on a straight line, we know that this angle is 180 degrees minus 90 degrees, resulting in 90 degrees. Area of the trapezium equals the upper side plus lower side times height divided by 2. On the other hand, the area of the trapezium equals the sum of the areas of 3 triangles. As these 2 areas are equal, we'll find out Pythagoras' theorem is proven after simplification. The proof was made by the President James Garfield, the 20th President of the United States in 1876. The ancient Greek discovered the relation with respect to the 3 sides of a right-angled triangle as early as 2500 BC, but the Chinese actually had similar discovery even earlier. Yes? Chinese oldest mathematics book, Zhao Bei Sun Ging, recorded conversation between Zhao Gong and Sun Gou in the early years of Zhou dynasty, or about 1100 BC. Sun Gou's answers included Ngao 3, Gu 4, and Yin 5. In ancient China, Ngao was the shorter side, Gu was the longer side, and Yin was the hypotenuse of right-angled triangle. That means if the 2 shortest sides of the right-angled triangle are 3 and 4, the hypotenuse is 5. That's what Sun Gou mentioned in Ngao 3, Gu 4, Yin 5. 3 square plus 4 square equals 9 plus 16 equals 25, which is 5 square. That is, Ngao square plus Gu square equals Yin square. It is obvious that the relation with respect to the 3 sides of a right-angled triangle is the same as that of Pythagoras' theorem. In China, such relation is called Ngao Gu theorem or Sun Gou theorem. Zhao Bei Sun Ging also recorded that around 350 AD, Xiu Song proved Ngao Gu theorem by considering the relation among the area of each triangle, the area of the square at the center, and their total area. The square with the length of hypotenuse C is composed of 4 same-sized right-angled triangles, and the square with the length of A minus B. Then the area of the square with the length of C equals C square. The area of the 4 triangles and the square with the length of A minus B equals 4 times AB divided by 2, plus square of A minus B. After calculation and simplification, C square equals A square plus B square. The generated equation is just Ngao Gu theorem. It
turns out that there are so many different ways to prove the Pythagoras theorem. Needless to say that it must be so useful that it has attracted so much attention.
That's correct. Okay, let's go. Pythagoras theorem relates to right-angled triangle. Study of right-angled triangle in geometry is very important. We can solve some problems in our daily life by using the nature of right-angled triangle. Here's a ladder leaning against the wall. The top of the ladder is 2 meters above the ground. The foot of the ladder is 1.5 meters away from the wall. Then, what is the length of the ladder?
It's so easy. Let's find it out by using a ruler to measure it.
Right, but we've just learned the Pythagoras theorem.
Oh, yes. Let me use it. Let L meter be the length of the ladder. L squared equals 2 squared plus 1.5 squared. That is 4 plus 2.25 equals 6.25. L equals the square root of 6.25, so L equals 2.5. Therefore, the length of the ladder is 2.5 meters.
Besides, we may use Pythagoras theorem to determine the location and the position of something. For example, a ship starting from point O sailed 12 kilometers due west to point A and then due south to point B. If point B was 13 kilometers away from the starting point, how far did the ship sail due south? Let D kilometers be the ship sailed due south. As the ship sailed due west and then due south, the angle OAB is 90 degrees for the triangle OAB. According to Pythagoras theorem, D squared plus 12 squared equals 13 squared. Then D squared equals 13 squared minus 12 squared, which is 169 minus 144. The result is 25. Square root of 25 is 5, so the ship sailed 5 kilometers due south. Now, if the height of the hall is 16 meters and the height of the classroom building is 24 meters, if the classroom building is 15 meters away from the hall, what is the distance between the top of the classroom building and the top of the hall? Let's think about it. Firstly, we make a drawing to mark the situation. Let X meters be the distance between the top of the classroom building and the top of the hall. BC is 24 minus 16 equals 8. It means classroom building is 8 meters higher than the hall. According to Pythagoras theorem, for a right-angled triangle, x squared equals BC squared plus AC squared. That means x squared plus 15 squared equals 289. Finally, x equals the square root of 289, which is 17. So the distance between the top of the classroom building and the top of the hall is 17 meters. However, do you know that Pythagoras theorem can be used in a converse way to solve some problems?
How do we use Pythagoras theorem in a converse way?
The converse of Pythagoras theorem is that if the sum of the squares of the lengths of the two shorter sides of a triangle equals the square of the length of the third side, this triangle is a right-angled triangle, and the angle opposite to the longest side is a right angle. In geometry, we often use the converse of Pythagoras theorem to prove two lines are perpendicular. Well, let me ask you a mathematical question and see if you understand or not.
Okay.
In the figure, AC equals 10, BC equals 12, and AD equals 8. D is the midpoint of BC. Can you try to prove AD is perpendicular bisector of BC?
Let me do it. If we need to prove AD is perpendicular bisector of BC, we need to prove the angle ADC is 90 degrees. Firstly, in triangle ACD, D is the midpoint of BC, so CD equals 12 divided by 2 equals 6. AD squared plus CD squared equals 8 squared plus 6 squared, which is 64 plus 36 equals 100. AC squared equals 10 squared, that is equal to 100. As AD squared plus CD squared equals AC squared, according to the converse of Pythagoras' theorem, angle ADC is 90 degrees, so AD is perpendicular bisector of BC.
Ms. Zhang, you have taught us so much about Pythagoras' theorem, but you still haven't taught us how to mark square root of 3 on a number line.
Be patient, let me tell you now.
Great!
To begin with, mark point A at the position corresponding to 1 on the number line. Draw a vertical line segment AB, starting from point A with 1 unit long, and then join OB. As OA is perpendicular to AB, angle OAB is 90 degrees. According to Pythagoras' theorem, OB square equals OA square plus AB square equals 1 square plus 1 square. Therefore, OB equals the square root of 2. Take O as the center and OB as the radius. Use a compass to draw an arc which meets the number line at C. As OC and OB are radii of the arc, OC equals OB. Hence, OC equals the square root of 2. By this method, we can exactly mark the square root of 2 on the number line. We can also use this method to exactly mark the position of other square roots. We just found out the position of the square root of 2 on the number line by using the method above. We may do the same, draw a right-angled triangle with a length of 2 sides being square root of 2 and 1. According to Pythagoras' theorem, the square of square root 2 plus 1 square equals 3. Then the length of hypotenuse equals the square root of 3. Draw an arc with the radius of the square root of 3. We can find out the position of the square root of 3 on the number line. We can use the same method to find out the positions of the other square roots on the number line.
Oh, we can exactly mark the position of the square root of 3 and the other square roots on a number line by using this method instead of using a calculator.
Let me see if you understand how to mark the square root of 61 on the number line.
Oh, 61 is a 2-digit number.
The sum of square of 2 numbers is 61, so try to think, what are these 2 numbers?
Right, let me do it. 6 squared plus 5 squared equals 61. Then we have to draw a right-angled triangle with OA equals 6 and AB equals 5. Draw an arc with O as the center and OB as the radius. Then we can find out the position of the square roots of 61 on the number line. The ladder is longer than the lift. It seems that the ladder cannot be put inside the lift.
Yes, it can be put inside the lift by leaning the ladder.
Oh yes!
The student is so clever. She knows that we shall lean the ladder. Let's calculate what is the longest possible length of the ladder that can be put inside the lift. If the height of elevator is 2.4 meters, length is 1.3 meters, and width is 1 meter,